Welcome to General Chemistry Laboratory with Dr. Garrison. This week we're going to be analyzing a copper compound to determine the percent copper. We're going to use two analytical techniques and compare those. So for this lab, what you're going to do is actually weigh out an amount of copper sulfate pentahydrate and dissolve that, and then precipitate it with two other compounds. One of them will be a indirect precipitation, where we'll actually precipitate the sulfate and measure the amount of sulfate that was present, and then in turn use the formula for the molecule to determine the amount of copper that was present. For the second reaction, we're actually going to form a complex with an organic molecule, salicylidoxine, and we'll precipitate that out, and from that directly precipitate the copper and determine how much copper was present utilizing calculations. So those are the two methods that we're going to do. So we'll make a product and we'll weigh those products, convert them to moles. Okay, so this is what we're doing in class at the same time. And once we get the moles of product, then we go from moles of product to moles of copper, or moles of product to moles of sulfate, then moles of copper, and then from moles of copper to grams of copper, and then we'll calculate a percent copper for each sample. Now, we also have learned another calculation where we are doing the percent composition of a molecule, and so we have the theoretical value from that calculation, what the percentage should be, and then we'll be able to compare the percentage that we have calculated through an additional step of calculation. All right. So the first reaction that you're doing is an exchange type reaction. And so what we see is that we have barium chloride that's dissolved in solution and copper pentahydrate dissolved in solution. And when the sulfate and the barium come together, then they're insoluble. And so it precipitates out and makes a solid. This is your product that you're going to weigh. The copper chloride and 5 waters are bystanders in this process. And in fact, we're going to be learning here in the next few weeks about ionic equations and ultimately getting to a net ionic equation. And so this is your introduction to that. And so this introduction shows the barium and the chloride broken down into ions, the copper and sulfate and water all separated, and then shows our solid barium sulfate still together because it's precipitated and staying together. And then our copper, our chloride, and our water are, well, they remain unchanged from either side of the arrow. So if that's the case, if things are unchanged to get to a net reaction, then what we would do is cancel all of those, and we would only look at the piece of the reaction barium plus sulfate yields barium sulfate. So this is a net ionic expression, and they're actually very useful in a laboratory. Sometimes for basic things like you go to the shelf to get an ion, and you're looking for, let's say barium nitrate, and we don't have any, and so we need a substitution, so we could actually use barium acetate. Both are soluble, and so in this case we just need barium, right? Well, here we use the barium chloride, and so any of those would work for this reaction to facilitate it. So when you get the product, the grams of barium sulfate isolated, as I said before, I'm going to go through this a couple times. I'm trying to repeat it enough times you'll actually hear me. And so, but you're going to take the grams of barium sulfate and convert it to moles of barium sulfate, and then to moles of copper sulfate, and then we're going to find the moles of copper from that relationship, and then grams of copper. And so once you get this grams of copper, then you can find the percent copper from the weight that you started with. And so that's shown down here, the grams of the copper that you found divided by the grams of copper sulfate, pentahydrate, and you're going to do this for beakers 1 and 2. Okay, so that's the analysis for runs 1 and 2. All right, and the second reaction. We're actually forming a complex, and so what we see here is that this is an organic molecule and it has an acidic proton on it, and when that acidic proton comes off in a basic solution, then that can actually join with the positive copper. And so what they do is they form a compound with copper, single copper, and 2 of the organic structures. I'll show a figure of that on the next slide. And so what I want you to do here is take this reaction. I want you guys to write a net ionic equation from this using the model from the first reaction. So that's a skill that we're going to start working on. And so I want you to make an attempt at that for this lab. All right. This may be helpful to some, but if I'm looking at the structure of the organic molecule, what I find is that this phenolic group has a hydrogen that can be knocked off by changing the pH, and when we do that, then we get a negative charge on this side. The nitrogen here also has a lone pair of electrons, and as the oxygen has a couple lone pairs, which also provide a negative environment for that metal to be attracted to. And so the structure looks something along this line, where the copper is oriented between the lone pairs, and then there's some hydrogen bonding that's occurring out on the edges there. So it makes a nice green compound, and so we'll precipitate that, and then we'll do the same math that we did before, where you calculate the moles of copper salicylidoxine, and then moles of copper, and then grams of copper, and then we'll find a percent copper from that. So there's a couple things that are important in terms of the procedure. Start with the second reaction, beakers 3 and 4, okay? And your partner is going to do reactions 1 and 3, and you're going to do reactions 2 and 4, okay? So you are actually going to have your own beakers. Between the two of you, you should have 4 total runs, and that way we can average those and improve our numbers a little bit. All right. Be sure and use the analytical balances when you're weighing these, and keep enough significant figures, and always label everything. And we're going to do analytical methods. Now there's a new method that we're going to talk about today. It's on down here at the bottom. We're going to vacuum filter, and so there's a filter that we use. It's called a Buchner funnel, and with that you need a sidearm flask that fits the stopper that's on the Buchner. If it goes down too far, it can actually pull in and it won't work. So make sure that it's fitted appropriately. You're going to need a piece of filter paper. When you get your filter paper, make sure that you write down the type and brand of it. And so then we take the filter paper, lay in the Buchner funnel on top of the holes, and then you grab the solvent that you're using for today and wet the filter paper. And so once you get it wetted, it will seat down tight on the funnel, and we're going to put a vacuum hose on it, and then we'll take that and hook it to the aspirators under the middle bench in that sink. There's some aspirators that will cause a vacuum or pull a vacuum, and so we'll do a vacuum assisted filtration for all of our solids. So you'll do 4 filtrations today using a Buchner funnel. All right, you're going to take your product and we're actually going to dry it for a week. So we're going to place that in your drawer on a watch glass on the filter paper, and you're going to have pre-weighed the filter paper so you'll know the weight before and after the compound has been put on it, and you'll calculate that in a week. That means the lab won't be due for 2 weeks, okay? You'll have to wait on that. But be aware, we will continue on and start a new lab also the following week, because it just takes a few moments to weigh. So we will move on to another lab. All right, just to go back through the mole math one more time before we quit. I said this verbally, but to see it in a picture, again, finding the percent copper in copper sulfate pentahydrate. For the second reaction, we're going to have the copper salicylidoxine. We're going to convert to moles the mass. We're going to convert the moles of the copper salicylidoxine to moles of copper sulfate pentahydrate, then moles of copper. From that we can get grams of copper, and so then you can find the percent copper in your analyte by grams of copper divided by the grams of copper sulfate pentahydrate that you weighed out. Multiply that times 100, and that will give you the percentage of copper in that. So that's the main calculation. So we're really practicing those. We're really going to try to learn those. The last calculation to compare both the methods I've mentioned, it's a percent error. And whenever you do a percent error, you'll take that experimental value, the one we just calculated, and subtract the theoretical value. And that's from a percent copper calculation that we've done in lecture. So you'll utilize that here. And then we'll take that and divide it by the theoretical value. Note that this is the absolute value, so that number is always positive when you do that calculation. So use this when you're answering the questions to compare the two methods. So this is some empirical data that's useful for that process. All right, one more time, you're going to work in pairs. Partner 1 do beakers 1 and 3, partner 2 do beakers 2 and 4. Each person gets to do both reactions, right? And then get the results from the other person. Make observations when they're doing theirs, and so that you have the results for 1, 2, 3, and 4. And you have to know how many grams of copper sulfate pentahydrate that you started with. You have to have that number, and you have to have the grams of product that was made to do the calculations. If you do that, then we can work you through the calculations. Be sure and come get some help if you need it. And in the tutor sessions or in my office. And then a couple things, don't touch chemicals. Just a reminder, we've got to wear our safety glasses, make sure that you got them on, and no food, drink, or water bottles or those types of things in the lab. Please leave those out in the hall, guys. And we'll have a container for the barium. It cannot go down the sink. And so that aqueous waste from the barium reactions, beakers 1 and 2, has to go in the container that we have in the hood in the back, and it will be appropriately labeled. If you are unsure, please ask me, and I will help you find where that goes. All right, the other solution can be disposed of in the drain. So, all right. We have some people who aren't finishing the labs completely, so just a reminder, fill in all the tables, right? The table of reagents, for example, the substance you need, and the amounts that are used after lab. Make detailed observations, right? Is it bubbling? Is there gas giving off? Is there a color change? What's the product look like? Describe it. And so we want to see some significant observations, right? Numerical observations too, weights and those types of things with units. Be sure to put units on all your measurements. Identify what the measurement is so that someone can read it who's never done the lab before and understand what you've done. All right, signatures. At the end of each block, we want your signature and a date. And so that's just a practice that happens in laboratory notebooks when you're in industry. Very often a supervisor then would sign it also, following your work. And so we're just trying to get you into that habit, okay? And then finish the experiment, all right? Calculations, dispose of the product in the appropriate place, and then turn in your experiment.